My name is Cheng from Rutgers. I will be presenting our work on Nitro, a capacity-optimized SSD cache for primary storage. And this is joint work with my colleagues in EMC Princeton, New Jersey office when I was intern there. Storage administrators have struggled with the complexity of primary storage architecture as performance and capacity requirements continue to grow. Given a limited budget, you really want to maximize performance and capacity while minimizing cost. For performance, we want high I/O per second, high IOPS, and low latency. In a typical unified storage environment, sometimes called hybrid storage, the storage system comprises hard disk drives, HDDs, and flash-based solid-state drives, SSDs. A common technique to accelerate performance is to place a SSD cache in front of the HDD storage, which can achieve much of the performance benefit of SSDs and the cost per gigabyte efficiency of HDDs. Although SSD caching has been researched over the years, there's a limited work on further optimizing the cache performance while considering the dollars per gigabyte. Since the cost of SSDs continue to be a large fraction of the total storage cost, further optimizing performance along the spatial dimension and the cost dimension is critical. Data reduction techniques such as deduplication and compression can be leveraged to improve space efficiency. For example, we can leverage deduplication to expand the effective cache size. By deduplication, we mean replacing repeated content with references. Previous study and our characterization results show that primary workload contains a large number of duplicates. So a content addressable cache can be used to improve space efficiency and reduce cost. The complexity of deduplication is that we need extra infrastructure to track the duplicate data and manage the fingerprint. We can also leverage compression to achieve high space efficiency. Previous work showed that compression can save 10 to 60% of capacity. Different than main storage, SSD caching should focus on performance rather than high compression ratio. So leveraging a LZ-style compressor can achieve low latency storage. The complexity of using compression is that it transforms fixed size data into variable size data. We need to figure out how to lay out data on the SSD effectively. In our work, we focus on incorporating SSD as a cache to accelerate disk storage performance. In particular, we present Nitro Cache, a caching system that leverages data reduction techniques to increase the effective cache size. We built our two Nitro prototypes on top of HDD-based storage arrays. The first used a capacity-optimized storage with deduplication and compression, which we call a COS system. The system is typically targeted for storing highly redundant sequential backups. Therefore, it has a lower random I/O performance, but it becomes a plausible primary storage system with Nitro acceleration. The second prototype system used a traditional primary storage, a system without deduplication or compression, which Nitro also accelerates. There are several design goals for Nitro that we should highlight. First, we use SSD as a cache to improve the overall cost efficiency. Second, because of increased effective cache size, Nitro achieves more than double performance compared to a SSD without Nitro. Third, using SSD as a cache generates more overrides. Nitro design reduces SSD erasures up to 65%, which increases SSD lifespan. Finally, Nitro requires extra RAM to index the SSD and to support deduplication and compression. Nitro minimizes RAM footprints as the system scales. Now, we briefly introduce some of the Nitro components and data path. First, we discuss Nitro key components. The file extent is the basic unit of data stored in the SSD, representing consecutive bytes in a file. Nitro references extents that are compressed and stored in the SSD. We use 8K as the default extent size to match the medium I/O size in our traces. The write evict unit, WEU, is our unit to replace and evict data for SSD. File extents are compressed and packed together into one WEU in RAM and shipped to the SSD when it is full. In write-back caching, we segregate clean extent from dirty extent. The granularity of cache write and the cache replacement is an entire WEU, which eliminates copy forward of live data during SSD garbage collection. Each WEU has a header section describing its content. The header can be used to accelerate rebuilding the RAM indices when system restarts. We use the generation numbers in WEU for consistency, and the paper describes generation numbers in more detail. Next, we look at how Nitro works. Nitro is conceptually divided into two halves. The lower half is HDDs and SSD devices. The top half manages cache infrastructure like indices in memory. The file index contains a mapping from file handle and offset to a extents location in the WEU. Multiple file index entries may reference the same extent due to deduplication. To support deduplication, we build a fingerprint index that maps from extent fingerprint to an extent location within the SSD. The fingerprint index allows us to find duplicate extent and effectively increase the cache size. We decoupled the fingerprint index from the file index to support adjustable deduplication. The example shows a client issuing a read request to our network-attached storage system. The request includes a file descriptor, offset, and size. Nitro looks up the file index and determines the extent is not cached. The cache miss will cause a read to the disk array. When the file extent is read from HDDs, the data is returned to the client. In a separate process, we hash the new extent to create a fingerprint, such as the SHA-1 function. Then we check the fingerprint against the fingerprint index. If the fingerprint is not in the index, then we compress and append the extent to an in-memory WEU and update the WEU header. Then we also update the fingerprint index to map from a reference to the WEU location, and also update the file index to map from file handle and offset to the WEU. We go along like this. When the in-memory WEU becomes full, Nitro increments the generation number and write it to the SSD. Now suppose the user wants to read the file again. A read request comes into the system and checks the file index based on file handle and offset. If there's a hit in the file index, Nitro will read the compressed extent from a WEU and decompress it. The LRU status for the WEU is updated accordingly. If there's a miss in the file index, but the underlying storage system support recipe cache, Nitro will prefetch file recipes into the recipe cache. The recipe is a component that represents a file as a sequence of fingerprints referencing extents. Capacity-optimized storage often has file recipes, while traditional primary storage typically does not. So subsequent read requests can reference the recipe cache to access fingerprint, which are checked against the fingerprint index. If the fingerprint is found to be a duplicate, then the cached data can be returned. Therefore, it can avoid a substantial fraction of potential disk accesses. Finally, let us look at how Nitro handles duplicate writes and overwrites. Once a WEU is stored to the SSD, we do not update its header in place because of high erase penalty. When a duplicate write comes in, we find it's a duplicate from the fingerprint index. A duplicate entry will be created in the file index that points to the extent location in the SSD. When Nitro overrides file extents, the file index entry is updated to refer to the latest version. Previous versions in the SSD may still be referenced by duplicate entries in the file index, and our paper explains other data paths in greater detail. Now we move on to methodology. We use the FIU traces to evaluate Nitro. There are 3 publicly available traces with content fingerprints representing server use cases. For example, the home trace is collected from home directory servers. We also included other traces which are detailed in our paper. We evaluate Nitro using both simulation and prototype systems. We use a detailed SSD simulator to measure SSD ratios. We further modify the flash translation layer, the FTL layer, to directly support caching to see how Nitro would be affected by potential SSD changes. We built Nitro into 2 prototype systems. As mentioned before, a capacity-optimized storage and a traditional primary storage. We built several cache variants to study the impact of our Nitro design decisions. We first classified these variants into extent-based and WEU-based, representing different granularities to interact with the SSD cache. We further built variants with deduplication and compression on or off to isolate the contribution of each data reduction technique. The WEU-based deduplication and compression version is the default configuration for Nitro. Now we move on to evaluation. We begin by showing Nitro's effectiveness at improving the rate-heat ratio. The figure shows the rate-heat ratio result for the home traces. We used 2% of the underlying storage system size as the cache size. We start the y-axis at 50% to focus on the relevant portion of the figure. The rate-heat ratio for the extent-based, no deduplication, no compression case is 55%, whereas the deduplicated extent-based version achieves 64% by reusing duplicate content. The WEU-based, no deduplication and no compression version has 53% rate-heat ratio, which is slightly lower than that of the extent-based version. This result shows a great insight that using a large eviction unit like the WEU does not hurt the heat ratio much. As we demonstrate in a moment, WEUs can effectively reduce the number of SSD ratios. The WEU-based deduplication version increased the cache size, but the heat ratio is slightly lower than that of the extent-based deduplication version, because the extent-based version has a finer granularity of eviction. Finally, the rate-heat ratio is further improved when both deduplication and compression are included. The other 2 workloads demonstrate the same trend. When incorporating deduplication and compression, the rate-heat ratio improvements are from 14% to 25% across all 3 workloads. Next, we study the impact of Nitro design on SSD lifespan. Nitro leverages write-evict unit to reduce write amplification. The figure shows the normalized SSD ratios across all 3 workloads. We compare the WU-only version, the WEU-based version with a trim command, and the extent-based version with a trim command. Lower numbers are better. A trim command allows the operating system to inform the SSD which data are no longer valid and can be removed internally. We found that the WU-only version can reduce the number of SSD ratios compared to extend-based version with the trim command. This is because the extend trim eviction has no knowledge of SSD layout. Therefore, it cannot completely avoid copy forward live SSD data compared to the WU-only version. Decreased SSD erasures directly translate to increased SSD lifespan. The WU trim version has SSD erasures close or a little higher than the WU-only version because of FTL implementation details. Although not shown here, we also considered moving the caching functionality down to the SSD FTL layer to see if it helps heat ratio or reduce SSD erasures. We found limited improvement compared to using the WEU. In the interest of time, I briefly summarize other interesting results. Because of more read hits in the SSD cache and canceled duplicate writes, Nitro system shows that a small heat ratio increase can translate to more pronounced IOPS improvement. Because primary workloads may have a wide range of content redundancy, the Nitro fingerprint index size can be limited to any arbitrary level to match the duplicate characteristics, allowing Nitro users to make trade-offs between performance, deduplication, and RAM footprints. Nitro has low overheads, with most of the latency devoted to decompression because it's always on the critical path for reads. Our sensitivity analysis showed that for a unified storage system, the cache heat ratio is important because the slow disk storage is the bottleneck for the overall performance. We also derived the effective cache size formula from physical cache size and deduplication and compression ratios. Because of deduplication, Nitro also accelerates snapshot restore if the old data overlaps with the already cached primary data. Deduplication reduces write traffic to SSD. Fewer SSD writes cause fewer SSD erasures, which means longer SSD lifespan. To summarize, we leverage deduplication, compression, and SSD performance to improve HDD-based storage systems. We proposed Nitro and demonstrated its effectiveness with 2 prototype systems. Nitro balances performance, cost, SSD lifespan, and resources. Nitro provides up to 120% improvement in performance and 53% write reduction to SSD. And that concludes my talk. Now I would like to answer your questions.
I forgot to say that Cheng is actually planning to graduate in the near future, so he's going to be on a job market.
Hi, Mike Cheng from University of Toronto. I was wondering what checksum functions what fingerprints functions are you using? Is calculating those fingerprints, the overhead of calculating those fingerprints is going to affect performance in real life?
The calculation of the fingerprint is completely off the critical path. We use SHA-1 function to calculate fingerprints.
So you're deduplicating in the background, not the critical path?
Yes.
I see. Thanks.
Hi, Hyong from Huizhou. Seems to me that he integrate the compression and deduplication in the SSD to improve the effective capacity, right? So obviously it's beneficial for the improve the IOPS, but what my question is that it is able to improve the individual request latency. For example, in other words, it is suitable for the QoS sensitive workloads. For example, especially when you use the compression, you have variable size because you compress them. So after reading out the compressed content, you have to go through the decoding and decompression process. So I wonder, do you have any results about this? How the individual request latencies that is affected by your
Compression is also off the critical path. And we introduced the concept of WU to pack those variable size compressed extent together and write it to the SSD. When read those extents, we read those compressed extent and decompress it.
Okay, thank you.
All right, thank you all for staying through the end of the conference. Let's finish by having another round of applause for all the speakers. Thank you.